With many tasks in the real world, a great technique for completing them is to break them into more easily accomplishable parts. Even mathematicians use this technique, and that's what we will be learning today. Hi, my name is Tom Atwater, and today we will be investigating integration by parts. So let's take a look at that formula. Integration by parts. If we have the integral of u dv, that is going to be equal to u times v minus the integral of v du. This formula expresses one integral in terms of a second integral. With the proper choice of u and v, the second integral may be easier to calculate than the first. In making the choice, we want u to be something that simplifies when differentiated, and dv to be something that remains manageable when integrated. Here's a strategy for choosing u. It's called lipit. What to choose for u? The first choice is, if there's a natural logarithm, use that. If not, go to an inverse trig function. If that doesn't help, then look at possibly using a polynomial for u, then an exponential function for u, and last, try to replace it or substitute it with a trigonometric function. All right, I think the best way for us to look at this would be to take an example and apply the formula. So let's take, for example, find the indefinite integral of x times sine of x. The way we want to do this then is to choose a u, which would make it easier. And so I'm going to choose u equals x. And then I'm going to, what that would leave us with is that dv would have to equal sine x dx. And that means du is equal to du dx is equal to 1, and therefore du is equal to dx. And then for v, we would have to anti-differentiate the sine of x, which of course gives us negative the cosine of x. So now we have the four parts that we need in order to plug them in to the formula. So we take u times v, so u is x, times v, which is negative cosine x, and then we subtract the integral of v, which is minus cosine x, dx. And so now what we can do is continue with the integration part of it, because we can integrate negative cosine x dx very easily. So let me make some room above here where I can continue this. And we can see that the first part becomes negative x cosine x. And then when we integrate here, the minus sign comes up, and when we anti-differentiate negative cosine x, we get sine x. Then we have our plus c. And so by making that an integration by parts, we made this x sine x dx a more manageable integration, something that we were able to do. Now, sometimes when you use integration by parts, you may have to use it repeatedly to evaluate the integral. Let's take a look at something like that. Okay, here let's take the integral of x squared times e to the x dx. And in this particular case, we're going to say that u is equal to x squared. And that means that dv is going to be equal to e to the x dx. So for du, that's going to be 2x dx. And for v, that's going to equal e to the x, since the derivative of e to the x is e to the x. So plug this into the formula u times v. So we have x squared times e to the x minus the integral of v, which is e to the x, times du, which is 2x dx. Of course, we can take the 2 and bring it out in front of our integral, so that what we have is x squared times e to the x minus 2, then the integral x times e to the x dx. And we're actually going to use integration by parts on this integral a second time. In other words, we're going to repeat the process. In this particular case, we're going to use the fact that u is equal to x. And therefore, dv equals e to the x dx. So du is dx, and v is e to the x. So once again, we now use the formula u times v minus the integral of v du. To do that, I'm going to have to create some space here. So let me eliminate just this line. And let me carry that up, so that we're going to have now that this is going to equal this line. And we want u times v, so u times v, x times e to the x, minus the integral of v times du. So that's v times dx. So we know that the integral of e to the x dx is just e to the x. Therefore, I know over here, I've just worked out this part up over here, and this particular section is just going to be e to the x. But now I have twice that whole product, twice that difference, because of the 2 that I need to put out here. So let me use a different color to show where we are. We have this with the minus sign, and I'm subtracting this part right here. So let me do that at the bottom of the screen, bring it all together for us. In the following final answer, we have the x squared e to the x minus then the 2 times x e to the x minus 2 times e to the x. After writing that, I realized that this is actually a plus sign, because we have the minus sign here and the minus sign there, which of course gives us the double negative for a plus. I have my plus c, which I have to add in because I am anti-differentiating. The last thing I want to do for you here is point out that each one of these terms has an e to the x in them. And if I factor out that e to the x, then I will be left with a quadratic, which is what I want to show you. And so I'm going to rewrite this just once more, and I'll rewrite it up here. so that my final answer will be e to the x, parentheses, x squared minus 2x plus 2, and then close the parentheses and add the plus c. So that is my final answer to the original problem of integrating x squared e to the x dx. And we used integration by parts twice in order to solve that particular problem. Now, this technique works for any integral in which n is a positive integer, because differentiating x to the n will eventually lead to 0. And of course, integrating e to the x is easy. Now let's turn our attention to solving for the unknown integral. So let's take this example. Use parts and solve for the unknown integral. And the integral we have is e to the x times sine x dx. So once again, we want to set up a substitution where we're going to use u. Let's say u is equal to e to the x. And that means that dv is equal to sine x dx. And of course, when we differentiate over here, we simply get e to the x dx. And over here, when we integrate, we get v is equal to negative cosine of x. So now we can put it into the formula of multiplying u times v. So u times v minus the integral of v du. Okay, so next we still have to deal with this. And so we will use integration by parts a second time for that part of this integration. So in this particular case, we're going to once again say that u is equal to e to the x. That leaves that dv is going to be equal to cosine x dx. Du is e to the x dx. And v will be equal to sine x. So now we can use integration by parts formula for this part of the integral, and we want to multiply u times v and then subtract the integral of v du. So this part here, I will rewrite over here, and it's going to be u times v minus the integral of v, which is sine x, times du, which is e to the x dx. So let me create my space, and I'll write v sine x times e to the x dx. One of the things I just realized is that when I set up my original or my second integration by parts over here, I had already considered that those had combined to a plus sign. So I need to put that in there because we're about to bring everything back together. What I mean is, right now, on the left-hand side, we have this integral. And on the right-hand side, what I have is this integral here, I'm sorry, this part, first part from integration by parts, which I now have to combine with this plus sign down to these two. But what I want to show you is, of course, that I have the integral of e to the x sine x dx on the left-hand side, but I also have the integral of e to the x sine x dx on the right-hand side. So it's as if I have a variable, which let's call the variable a. I have a on the left-hand side, and I actually have negative a on the right-hand side. So I can add the negative a, or add the a to both sides, leaving me with 2 of them on the left-hand side, which I will write down. And just to show you where we're going, that means on the right-hand side, that is left over after I add the a to both sides, I will have this e to the x times negative cosine x plus e to the x sine x. So that's what's going to be on the right-hand side of my new equation. So what I'm actually going to do here is erase this whole screen and rewrite my 2 integral of e to the x sine x dx, 2 of these, equaling e to the x times negative cosine x plus e to the x sine x. So let me do that. Get rid of this and rewrite it like this. 2 integrals of e to the x sine x dx equals negative e to the x cosine x plus e to the x sine x. And therefore, I can now treat this like that variable a and solve for a by simply dividing both sides by 2. So I get the integral of e to the x sine x dx is equal to negative e to the x cosine x plus e to the x sine of x all over 2. And by doing so, what I have done is solve this integral for, that is, solve the integral of e to the x sine x dx by using integration by parts and then solving for the unknown integral. And so this would then be my answer for that integration. So it's a neat little technique of solving for that integral with using integration by parts a couple of times and then treating that as a variable which we then solve for. All right, great. Let's examine now an example of tabular integration. So let me bring up this example, the integral of x squared e to the x dx. And what we're going to do is look at setting up a table where we have f of x and its derivatives. And f of x is going to be x squared, which you can see right here. Then we're going to have g of x start off as e to the x, which you can see right here. And what happens is on the left-hand column, we take its derivatives. So we have x squared goes to 2x to 2 and down to 0. On the right-hand side, we integrate the e to the x. In other words, the integral of e to the x is e to the x. The integral of e to the x is e to the x. And the integral of e to the x is e to the x. And now what we can do is actually find the solution to the original integral problem of x squared e to the x dx by combining these products following the arrows and using alternating signs starting with a plus sign. So let me show you that. We have the integral of x squared e to the x dx. And that's going to be equal to taking x squared times e to the x squared e to the x. And it's positive with that positive sign. Then we're going to have minus, because of the minus sign there, the product of 2x and e to the x. So minus 2x e to the x. And then I'm going to have 2, or plus 2 e to the x. 2 e to the x. And of course, because it's an indefinite integral, I have my plus c to add on at the end. So if you remember, we actually did this problem earlier. This is the solution we got by using integration by parts, but here was a way of using a table to help us separating it out into two different parts, again, with an f of x and a g of x, but using a table in order to help us integrate that. So that's a good example of another technique we can use to integrate an integrand which is not necessarily clear how to do so at the beginning. Let's do another example which involves logarithms. So let's look at that right now. I want to find the integral of log x dx. Now, you may say, wait a second, we were given a formula for this already. We already know how to do this. But what I want to show you is, by using integration by parts, how we came up with that formula. So what we'll do is this. We're going to let u equal log of x. And therefore, dv will equal dx. And now, du equals 1 over x dx. And v equals x. And therefore, my integral becomes the integral of log x dx becomes u times v. So u times v, but I'm actually going to write it as v times u. So x times log x minus the integral of v, which is x, times du, which is 1 over x dx. But then you'll notice what happens, of course, is the x's will cancel down to 1, so we're really just integrating dx. Well, the integral of dx is, of course, x. So this will equal x log x minus x, and then we have our plus c for the indefinite integral constant. And therefore, we have just shown how we came up with the formula for the integral of log x being x log x minus x plus c. Now let's turn our attention to finding for an inverse trig function. So let's find the integral of arc cosine dx, or in other words, cosine inverse x dx. In this case, we're going to let u equal the inverse cosine. In other words, arc cosine of x. That means that dv is equal to dx. And du will be equal to negative 1 over the square root of 1 minus x squared dx. And that comes from the formulas that we learned earlier about the derivative of the arc trig functions. V is then going to be equal to x. So now, using the formula for integration by parts, we can say that this integral is equal to u times v. So u times v, so x times arc cosine of x minus the integral of v, which is x, times du, which is negative, so I'm going to put the negative up there, the square root of 1 minus x squared dx. And now what I'm going to do is be able to integrate this particular one because we know how to integrate that particular function. So the first part doesn't change at all. We have x times cosine inverse x, and then this is going to be minus 1/2, and I'm going to put negative 2x up here, and you'll see why, as I explain through this, that square root of 1 minus x squared and my dx. Because now what you'll see I'm doing is I'm setting this up so that I can do a substitution and integrate this using a substitution of u is equal to 1 minus x squared. Because if I do that, then du is going to equal negative 2x dx. So let's write that up above here, and I'll show you that. What we have is u equals 1 minus x squared, and du equals negative 2x dx. So that what I have is this being equal to, of course, the x cosine inverse of x doesn't change at all, but then what I have is minus 1/2 the integral of, well, what it actually works out to be is u to the 1/2 times du. Or that's u, I'm sorry, u to the minus 1/2. There we go. So now we do know how to integrate u to the minus 1/2 du. So let me erase one more line here to give me that space. And what we have then is, again, the x arc cosine x doesn't change at all. But now this is simply going to be equal to, we have to add 1 to that, so it's u to the 1/2. It's still going to be minus, so that we have the minus 1/2 out in front, plus, of course, the capital C. The last step for this, then, is to make my substitution back again. And that is, we know that u is equal to 1 minus x squared. So this will equal x arc cosine x minus the square root of 1 minus x squared. Then I have my plus c. And so that's my final solution to the original integral of arc cosine of x. All right, great. Now it's time for you to try a problem. What I would like you to do is find the integral of arc sine x. That is, integrate sine inverse of x. So pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Okay, this problem was similar to the example that I just did, and so you want to set it up in the following manner. You start off by saying that u is equal to sine inverse of x. U equals arc sine of x. And that, therefore, we're going to say that dv is equal to dx. And then we say that du is equal to 1 over the square root of 1 minus x squared dx. And that v is going to be equal to x. And so when we plug this into the formula, we get that this is equal to u times v. So x sine inverse of x minus the integral of x over 1 minus, over the square root of 1 minus x squared dx. Now I want to do a little algebraic manipulation to set this up. We'll leave the x arc sine x alone, but what I'm going to do is change this to plus 1/2 of the integral of negative 2x on the top. So the negative 2 takes care of the fact that I changed this to plus, and it takes care of that 1/2. And on the bottom, we still have 1 minus x squared dx. Now, the purpose of that was just like the other problem we did earlier, which is I now can do a u substitution. And I need some space, so let me erase my original integration by parts. And what I now have is this. I have that u is going to equal 1 minus x squared. Actually, I'll do it right here. U equals 1 minus x squared. And therefore, du is equal to minus 2x dx. So that what I can do is rewrite this as equaling x arc sine of x minus, plus, because I have a plus, 1/2 of u to the minus 1/2 du. And let me put my integral sign in here to show that we're going to integrate that now, so that we have still x arc sine x. And now what we have is plus u to the 1/2 plus c. And my final step then, of course, would be to substitute the fact that u is equal to 1 minus x squared. So let me erase what I have here to make room. And my solution then is going to be that the integral equals x arc sine x plus the square root of 1 minus x squared plus c. So if that's the answer you came up on that problem, you're well on your way to understanding how to use integration by parts with substitutions involved with it. Great job today. So in this section, we used the product rule for integrals. We looked at substitution as a method for solving them using integration by parts. Be sure to work the exercises that your teacher assigns, and we'll see you next time.